So, hello everyone. Hope you had a good lunch. We're back for the afternoon of the second day of the workshop. Now we'll have a talk by Júlio on GeoStats.jl, Advanced Geospatial Data Science with Júlio. With Julia. Thank you.
That was a good one. It works too, right? Yeah. Wow. Okay, good afternoon, everyone. Let's go for the second talk. So I have some examples that are also run like we did in the previous talk, and a couple of slides as well. I will try to repeat the same format where I will follow the slides, and then at the end I will just show some of these examples running live, so that you can also get this access to these scripts after the talk to run them by yourselves, right? But I want to really like focus on the slides together, and then you can look at all these concepts together, because looking at the same time at code, at slides, at the presenter, and trying to absorb all these things at the same time, it doesn't work. So just go with slides first, then examples, and then we open questions and discussions, right? So Advanced Geospatial Data Science with Julia. And we'll be learning about this framework here called GeoStats.jl, which is a package that puts this framework into software, right? So let's learn about this a bit more. So what is geospatial data science? So if you try to work with geospatial data, you often have to do a lot of manipulation, processing, visualization, statistical analysis. And if you merge all these things together into an umbrella, that's what we are calling here geospatial data science, right? So it's manipulation, efficient manipulation, statistical analysis, and visualization of geospatial data. I would like to point out that when you call something a framework, it means that it's not just a bunch of disconnected things put together into a bag. It is a way of thinking, right? So you have to really organize how you process and how you manipulate your geospatial data in a very structured, organized way, right? So that's what we call a framework. And this framework is described in a corresponding book that I also share here, and it's materialized in the software. But so a framework is a way of thinking about this geospatial data, how you manipulate it, how you process, how you visualize it. It's not a set of data types in a language. It's more than that, right? What is it not? Also, it's not a one-off, hard to read script. So you see like a lot of data science is done, and you see, depending on the background you have, if you're not a computer scientist or someone that's used to write a lot of code, you end up doing like these one-off scripts that you throw away later because it served for a specific purpose, and then you just rewrite something in the next project and you rewrite it again. We really want to make you learn this framework so that you write very general scripts that you can reuse many, many times with different types of geospatial data and so on and so forth. And also, like, there is this, I don't know if it's true or not, but sometimes like there's this culture that like data science scripts are slow, they don't run enough at enough speed because they're not written by experts that know their low-level hardware. We also want to take this message out of the table. We want to make you guys able of writing very high-level scripts that run fast. And that's the whole idea behind the Julia language, to make this technology more accessible to non-experts in computer science, but experts in science, right? In geoscience, for example. So before I jump into the geospatial data science problem, which is a problem of, let's say, data manipulation, right? I have this other problem here that I'm bringing to the table. The Julia language has a famous problem called the two-language problem. Here, I'll do a variation of this problem, is the two-team problem, which is basically you have one mindset, which is the software engineering team. And if you read the bullets here, it's basically a summary, a high-level summary of what's going on in the mindset of a software engineering team, right? So you usually write code that's very sophisticated in design. It has very sophisticated design patterns. It has attention to the minor details, right? So you handle all corner cases, performance. You're like really into the code. You have functions that address very low-level tasks. So the software engineering team is usually cares a lot about these minor details, low-level tests that need to be very, very high performance. but they rarely touch scientific questions, right? Because they are mostly involved with this task of getting the infrastructure for the scientists to then answer the questions, right? So these people, they are, if you put in a pyramid, you have the people at the bottom doing the infrastructure and the people at the top doing the, let's say, the more high-level science, right? The scientific questions in climate, in earth science, and so on. If you look at this team at the top, the data science team, let's say the scientists that are trying to do science with programming, they have a different mindset, right? So they usually write code with data analysis in mind, right? So they want to do something that has some specific data analysis patterns. They have attention to the big picture. They want to answer the question. They don't care about the minor details or the corner cases of the code, if it's going to break if you feed something that's not valid. And so because they are also handling these high-level tasks, which are like more related to the scientific question, they don't consider too much the hardware, right? So they usually like write scripts that get their scientific questions addressed, but they're not experts into writing the most performant code to run on a GPU or to run on a multi-core CPU, and so on and so forth. So we call the development mindset in the left the performance-driven development, right, which is focusing on performance and hardware, and the one in the right, the question-driven development, right? So these are two mindsets, two teams, and we really want to try to bridge this gap, which exists, right? It's very well known with technology, right? So Julia is one of the things that we are really like trying to push over the years as a technology that bridges the social gap between these teams. Besides the technology itself, it bridges different teams together. So in the specific case of geospatial data science or geospatial processing, right? So we are trying to do this for the geospatial data science community, right? So we created this framework, which is a way of thinking about geospatial data that tries to unite these two words. So there is it was carefully designed to unite these efforts of software engineers with data scientists, right? So you can, as you see some of the examples here in a few minutes, we write very high-level code, but if you need to get more performance, we let the people write new blocks or components that we call transforms and different things in the framework to get more performance. So different people can interact at the same language with the same level of abstraction, and if they need to go low level, they also can. So it was made after years of development, right? So that's not something that started yesterday. We've been developing this for years. I think it's maybe a decade already. I don't know exactly how many years, but it's a long time. And anyone, I think it's one of our personal goals here in our agenda is anyone with basic programming skills that can read high-level Julia code, high-level Python code, can potentially become a contributor, right? Because it's 100% Julia. We don't access very low-level memory patterns and buffers and all these things. We really write everything in Julia, and it's usually easy to understand. So we want to keep it that way. There's lots of work to do still because, of course, we're a small team. There's not many people working on this. We hope to get more and more contributors over the years, but because of the small team, we cannot handle all corner cases, right? So sometimes in a corner case, things won't be as fast as they could. So we ask help for people. So, hey, this is not working with the speed I want. Submit a contribution. We are happy with this. But I'm just setting expectations here because sometimes you probably load a very big data set and things are not as fast as you imagine. So that's probably because no one optimized the block that you are trying to use, right? And I think the main resource to learn this is the book, right? So I will cover in this talk today one chapter of the book, but the book is open access. I already shared in the previous talk. It's online. You can Google for Geospatial Data Science with Julia. It will show you the URL that you can access all the chapters that are already available. So as I mentioned, like the topic of this specific talk here is one chapter of the book, which is about lazy pipelines of geospatial transforms. I will undo all this fancy vocabulary and explain what this means. But basically, we'll be able to take a geospatial data set and convert it, process it into different geospatial data sets. And if you followed the previous talk, This geospatial data set will be a geotable. You get this geotable, will feed into a sequence of transformations and get a geotable at the end. That's the whole idea. So what's the geotable? Very quick recap from the previous talk. A geotable is this attempt to arrive at a universal representation of geospatial data that generalizes all types of domains that you encounter in science, right? So raster, vector data, 3D unstructured meshes in physics and climate models, etc. It behaves like a table, but it's useful for statistical analysis. We design a bunch of features in this table to handle statistical analysis code, right? So we've seen some of this before, like it knows about scientific types, categorical, continuous types. It knows about units, right? So if it's in meters, in kilograms, all these things are useful for the data science test that you need to do. And it's made of two things, the values and the domain, right? So I think the most important bit of this review here is you need to remember that a geotable is made of a table of values and a domain, which is stored in the geometry column. So these two names here will be used in the next slides. The values of the table is of the geotable is the table of measurements, and the domain of the geotable is the physical domain, right? So I'm illustrating in the right here one such domain. So let's talk about these pipelines of geospatial transforms, what they are. There's this sentence here at the bottom, right? So they're powerful manipulation and processing of geotables, but what that means exactly we'll see now. So before we jump into these examples, let's categorize these transforms into three main kinds. There's feature transforms. These are ones that consume your values. For example, you have your geotable, you look at the values or just the measurements, you operate on these values and you return a new geotable. Geometric transforms, on the other hand, they operate on the domain of the geotable, right? So you have your geotable, you concentrate on the domain, you operate on this domain, rotating the physical region, stretching it, doing something with the physical domain, and returning a new geotable. And there's this more general class, the geospatial transforms, which is a mix of the two. It can both take the values and the domain at the same time, do some operation that involves the two, and return a new geotable. So these are the three classes that you're going to cover here. So feature transforms, right? So as I mentioned, a feature transform is just like a function that takes the values of the geotable and produces a new set of values over the same geospatial domain. We divide this feature transforms into three subclasses: basic, cleaning, and statistical, and these are the same ones that are described in the book. So what I'll do here, I will switch to the VS Code again, as I did in the other talk, and I'll show some examples of what these feature transforms are. I don't know if the font is too small or it's too big, but hopefully you can see something. If you don't, maybe you can access the link on YouTube, right, for the live stream. But here what I'm doing, I'm loading the framework, which is this main module here, GeoStats. It reloads every single thing you need to do for geospatial data science, including the geotables package we've seen in the other talk. I'm also loading Maki, which is the previous presentation we saw from Simon, right? So I'm loading the GL Maki backend that Simon presented in the previous talk before lunch. And what I will do here, I will start creating a example geotable, right? So what I'll do, I'll create N, capital N samples, in this case 10,000, samples with 4 columns. So I would say variable A is made of these values, variable B is made of these values, C and D. I'll place all these columns into a named tuple, which is one of the built-in table types we've seen in the other talk. That's a valid table in Julia. And then I'll georeference this table on a domain. In this case here, I'm using a Cartesian grid with 100 by 100 pixels, right? 100 by 100 quadrangles. So if I execute this code, you see here in the right, let me hide the files to get more space and execute it again. Oh, sorry.
Sorry, can the YouTube screen switch to the screen?
Switch to what? Sorry, Alex?
It's just the YouTube screen that's like this. So you can see the screen.
Oh, so it's not on me. I think it's on the people organizing the... because I'm already sharing there.
Yeah.
So the slides are... my screen is not showing apparently in the YouTube stream. Is it? It's okay? Perfect. Perfect. Oh, got it. But you guys get it now on the stream, right? Okay. Perfect. I just need a confirmation. If it's already on the stream, I can continue. It's on the screen? Awesome, awesome. So what you're seeing here, let me just repeat this part because some people online may not have seen, right? So I'm loading the main package here, GeoStats.jl, which is the package that reloads the whole stack. And that will be the only thing you need to import if you are wanting to do geospatial data science in Julia, right? So if you import this package, you can also import the GL-Mackie package, which is one of the backends that Simon presented in the previous talk. And in the second cell here, what I'm doing is I'm creating a geotable, an example geotable. So I create 10,000 samples. I create 4 synthetic columns, right? So variables A, B, C, D. And I choose a specific distribution of these columns we'll see soon. I place these columns into a named tuple, which is a valid table type in Julia. And then I georeference this table into a Cartesian grid. That's the domain, right? So if you do this, you'll see here in the right, in the terminal, there are 4 columns with features, the values of the geotable, A, B, C, D. And there's an extra column here with the geometry. I should probably reduce this even further so that you can see. Let me run it again. It's still not possible because the screen is so small here. Let me try it again. Okay. Now at least you can see the header here, the geometry, right? So you have 4 features in the values of the geotable, and you have the domain here represented as the geometry column. Now say I want to visualize what is in it in this geotable, right? So I can load, for example, one package that's very, very useful is pair plots. Pair plots is useful for multivariate analysis, so it can take any table in Julia and produce these plots called corner plots or pair plots. In order to do this, what we'll do, we'll take our geotable, I will extract just the values, just the subtable with features, and I will send it to the pair plot. So if I run this here, you should see a plot opening up here on my other screen. Oh, it's not going to be full screen. Yeah, I should probably, the resolution of my tablet's not allowing you to see everything, but you can see there are 4 variables, A, B, C, D, and if you plot these variables together, you see this multivariate distribution, right? So you see these shapes with 2 modes and these elliptical shapes because some variables are Gaussian, some variables are multimodal, but this is just an example data set that we use an example as to run some of these transforms, right? So this is a random geotable. Another way that I would like to show you that really, let's say, streamlines the syntax and makes the scripts very readable is use the Julia pipe operator. So you see this beautiful arrow here in VS Code. That's something that VS Code does, but you can get this symbol by pressing vertical bar. My keyboard was misconfigured, sorry. 1 second. It's in Portuguese, I want it in English, okay? So if you say vertical bar and then you write greater than, Julia, the VS Code editor will just merge the two into this beautiful arrow. And then if you use this arrow, Julia will just feed what's in the left of the arrow to the right and continue doing this. So I'm feeding the geotable to the values function to extract the features, then feeding the result to the pair plot. So it's equivalent to this line here. I'm just showing this because we'll be using this a lot in the next examples, right? So let me just execute this code here so that you see it works the same. So it generated the same figure we've seen before, right? So I'm sending the geotable to the values to extract the features. Then I'm sending it to the pair plot function to generate the pair plot. Now let's do some basic feature transforms. So what would be the most basic transform you can do with a geotable? Most of the time you need to select a subset of variables for your analysis, right? Sometimes you have tens of variables and your analysis only depends on a subset of these variables. One such transform is the selection, right? So you say, send my geotable to the select of A and B. If I run this code here, as you see, it will just take the two features that you care about. So it is going to discard C and D, retain A and B, and the geometry column. So everything retains the geospatial information. It's never lost. I can also say, just return the three first features, right? So I can just take this geotable and extract ABC. And there are very fancy selectors we call, right? So you can use a regular expression that says, return all the columns that have B, C, or D in their names, right? So I can just do this and it will just take the features of interest. I can also select and rename at the same time. So these are all examples that you can find here in the book. I'll share the script later. You can select column A and rename it to capital A. Select column B, rename it to capital B. What it will do is it will do the same as the selection, but it will also rename. You see now that the columns have capital A and B. Or you can also do the, let's say, the opposite operation, which is reject. Instead of select, you can reject columns. So I can reject the feature B and retain A, C, D. I can select A and send it to the viewer. Remember, in the previous talk, we saw ways of visualizing geotables, right? So if you select a feature and send it to the viewer, it will just create the visualization of the variable you care quickly, right? So you don't need to write a lot of code to just quickly inspect what you want to see, right? So here, I selected variable A, send it to the viewer, and now you have this grid with this random distribution that I created, right? So it's a Mackie visualization with the interactions that Mackie supports, and it's very convenient for quick exploration. Now let's go to another example of basic feature transform, rename. So instead of selecting and renaming, you can just rename columns. That retains all the other columns without dropping them out, right? So I can rename A by capital A, B by capital B. It will still retain column C and D because I'm just renaming, I'm not selecting, right? So you see now that A and B are renamed and C and D are retained. You can do a function on each of these columns of interest or in all columns. So there's this functional transform. So I will do here, I will send the geotable to the functional that applies the cosine function over all the values. And then I extract the values and send it to the per plot. So you see now that the multivariate distribution has changed, right? So if I show here the multivariate distribution of this geotable, it has a different multivariate distribution produced by the cosine function on the original multivariate distribution. Another very useful basic transform, these are all basic data manipulation, right? So you probably can do all these things in many different ways, in many different languages. What we try to do here is a set of transforms that's abstract and data independent so that you can express yourself just in terms of these transforms and then feed later any geotable that you have. So the map, the rename, the select, and all this, they are pretty much like independent of the data. You express what you want to do and then you feed the data later. I'll show examples of this moving forward. But the map here, what it does, it takes the column A, applies the psi function, takes the column B, applies the cosine function, and renames the result to cosine of B, right? So if you just execute the cell here, you see that it retains the original columns, A, B, C, D, but it creates a new column, A underscore sine, because I didn't provide a column name, and it creates a new column, cosine of B, which is applying the cosine to the column B and renaming the result to cosine of B. There are many other ways of selecting columns as well, right? So you can do map of columns 2 and 3, and then you get a function that takes the two values of the columns, right? So a value of B and a value of C, return an expression, and it will apply this expression to this selection and return a column that I'm naming here as f of BC. So this is another example. And to finish this set of basic feature transforms, we have the filter, which is also very useful. It's filtering some of the rows of the geotable based on some predicate function. So I can say filter all the rows for which the value of A is smaller than 0 and the value of B is greater than 0, for example. And if I just execute this, you'll see that it will return this geotable over this subset, right? So here, I'm taking the result, and you see that it's less rows than the original geotable, right? Oh, I'm executing a bunch of random code here from another script, so let me just clean here. Okay, so if you execute here this again, you see the result. And the other one that I would just like to point out here is sorting, right? So you can just sort the rows of a geotable based on columns of your interest. And there are many keyword arguments that you can pass to all these transforms. They're all documented in their respective doc streams. What's another very common operation that you need to do in data science? Sometimes you get a data set that comes out of raw sensors, raw measurements, and the variable names are terrible. Like, I mean, I don't understand why, but every device chooses a very weird variable name. It is never readable to a human, right? It's always very garbage, underscore, hash. It's very complicated. So data science starts with like clean the data as much as you can, filter all the things that you don't care, and then start your analysis. So cleaning transforms are very useful. One of them is, for example, the selection and renaming of these variable names, right? So for example, here, I will create a geotable with very weird names. So here is a geotable with a column called, a variable called ABCD-F and another column called B_2 parentheses 1. So this is like random names that could come out of a device or something like this. Now I want to standardize these names because, I mean, as a human, I want to process and report results in more readable names. So there's this transform called SDD names, where you send the geotable there and it will just like try to convert these names into a standard. There are many supported standards. The default one, I guess, is uppercase separated by underscores, but you have all these standards, for example, upper camel. And then you say, okay, I prefer to use upper camel. I prefer to use upper flat. And it will just rename the variables to a standard that you are more happy with. And you have all this documented as well in the doc strings. Another very useful cleaning operation is replace, right? So sometimes you have geospatial data or geotables like this one here at the bottom with missing values, for example, none, right? Not the number, or missing, or -999, because that's not a valid value for that variable. For example, it's a porosity or permeability or something that cannot be negative. They usually use a negative value to signal that this is a invalid measurement. So one thing that you can do is replace all these symbols on the geotable with the replace transform, right? So you can say replace -999 by missing and none by missing, right? So what we'll do is just like do this replacement for you. And the missing is a special value in Julia for missingness, because this is a very scientifically driven language, right? So they have a built-in type for missing from statistics, and so you usually want to convert all these low-level representations to something that's for sure missing, because that has a type that Julia understands and will allow you to do more fancy stuff with these missing values. Another way that you can replace values is by providing a predicate function. So in Julia, when you type smaller than 0, for example, it creates a function that takes 0 and something else and returns the result of 0 is smaller than something else, right? So what I'm doing here is I'm saying replace anything that's smaller than 0 by missing, right? So that's one way of performing this replacement. But you can feed in here any predicate function that returns true or false depending on a condition to replace the value. So I replaced the -999 by missing, but I left the num untouched. Another operation that's very useful, which is similar to replacing missing values, is the coalesce transform. The main difference here is that coalesce will also change the column type. So if you replace missing by a number, in Julia everything is typed by the compiler, right? So if you create a table that has a column of 1, 2, 3 missing, the column type of this table will be a union of missing and float, for example. If you want to make sure that no missing value can be stored in the future, you coalesce this table so that it removes the missing and puts something else there, but also changes the column type to be just a column of float. And that's more restrictive and important sometimes, so that you make sure that your script never reintroduces missing values, right? So if I say here the type of the column A, it will be just a vector of int. Whereas if you have used replace the missing by something else, the column type will still be a union of missing and something else. Another very common one is drop missing, right? So I should have scrolled here actually. So the coalesce I just coalesce with the value 2, right? So to replace missing by 2. But you can also drop the missing, right? So you can just feed this geotable into the drop missing transform, and it will just drop all the rows that have missing values in all variables. And you can also select specific columns of your interest. So let me just get back here to the deck of slides, because maybe I'm close to the time here. So let me get back. No, yeah, I'll proceed with just a few more here. So the final one that is still considered a feature transform is statistical, right? So if you look at a lot of these statistical transforms, for example, principal component analysis, factor analysis, I don't know, sampling the geotable in specific locations, or centering the distribution, or calculating the z-score, all these statistical transforms can be performed. They're also considered feature transforms. And so here I will just sample, for example, a subset of 1,000 pixels, right? So here, if you look at the code, I say, hey, I have a geotable which is over a grid. It's a raster. I will sample 1,000 of these measurements, which actually corresponds to 1,000 quadrangles, without replacement. After I do the sample, I just send it to the viewer, and you see that it produced that figure here, right? So it automatically changed the domain from a grid to a view of a grid and send it to the viewer. So you see here now that you have a collection of random pixels selected with this transform. You can also describe here a transform, right, to get some basic stats like mean, describe a geotable to get the mean, minimum, median, and other summary statistics. But you can also send it to the center. For example, I'll center variable A so that it has 0 mean, and I'll send it to the describe function again, and you see that the mean now is 0, right? So it's 10 to the minus 16, right? So it's effectively 0. There are many other similar ones like mean max. Instead of centering, I just scale by the mean max values of the columns. I can compute the z-score and so on. These are very similar. And the STD feature fits transform just tries to standardize all columns regardless of their scientific type. If it's continuous, it will probably use I don't know if it's the z-score or if it's the mean max. And if it's categorical, it will leave the column as is, and it does something differently depending on the scientific type of the column. There are many more here. For example, the quantile transform will take your multivariate distribution and take each variable and convert to a different distribution from the distributions package, right? So I can send my multivariate distribution to the quantile, and by default, it's the normal distribution. And if I send it to the pair plot, you'll see that all those multi-modes that you've seen in the original data set are gone, right? So there are the two modes that we had here kind of collapsed into one because we are trying to get each of these dimensions, A, B, C, and D, convert into a Gaussian. And when you plot them together again, you lose some of these multi-modes, right? So that's the idea. So there are more here, coerce and others that are also very convenient for people working in machine learning and all these areas, right? So for example, if I create here a geotable, let me create here this ST geotable. This ST geotable in the example, it has a column A, which is categorical, and a column B, which is continuous, right? So what you can do with categorical columns is many things. So you can do, for example, change the levels of the categorical array, right? So you say, I have a vector of categories A, B, C, D, but in my data set specifically, only A, B, and C appeared. So if you want to increase the number of labels, you use this level. So I'm increasing here to have levels 1, 2, 3, 4, right? That's something that is done internally so that you can do correct classification with the correct labels. You can also do a one-hot transformation, which is very useful when you're handling these neural net-based models, which handle these 0, 1 arrays as indicator functions, right? So if you go one hot here, one hot of A will take the column A, which is made of 1, 2, 3, and you split it out into 4 columns for each of the levels, right? Because I set the levels from 1, 2, 3 to 1, 2, 3, 4. I have 4 levels now for this categorical array, and it breaks the 4 levels of variable A into 4 columns of zeros and ones. And that's very useful sometimes because you need to train a model that expects arrays of zeros and ones. There's also this indicator transform. It takes a continuous variable and creates categories, splitting into different subintervals. So you You can split into a linear scale or a quantile scale. It's also very useful sometimes. So you get here column B, I split it into 3 intervals. Sometimes you have continuous data that you need to quantize, and that's what this indicator does. And basically that is the set of feature transforms that are explained in this example. There are more in the framework and more in the book also. So let's get back here and move to the second set of transforms. There are many of them. As I'm explaining here, this is one chapter of the book, right? So transforms is so many things that we don't have time to cover all the stuff here, but just the transforms will be something to know. But geometric transforms, do you have a question, Sebastian?
Yeah, to what you just talked about just now. When you want to do machine learning or deep learning with geospatial data, it's often very annoying to make a correct distribution, both in terms of geographical location and whatnot. Is that also easy to do with the view tables?
You mean like converting the features into this?
Make sure that in my training set and in my validation and testing set, I have specific type of geographical locations and
doing splits geographically, right? So yeah, we have partition methods as well, like they're more low level, you have access to them. So when you do, like, for example, a group by variable, that's one type of partition that's kind of non-spatial, but you also have other kinds of partition that work with, I want to partition this data set by a vertical plane. I want to split this data set by different spheres that don't overlap. There are so many different partition methods implemented you can look up and can discuss later. But you can take a geotable and split into test validation that are geographically split, right? So that's also possible. So geometric transforms here are the ones that operate not on the features, but on the domain, right? So you take a geotable, you want now to transform the domain or the geometry column. These are the ones that take the geometry and produce a new geometry column in a way that's not materializing the geometries, right? So it's smarter than that. And we can divide these geometric transforms into 2 types as well, coordinate transforms and advanced ones. I call it advanced because I couldn't find a better name, but coordinate ones are the easiest ones to understand, and there are ones that are most popular in geospatial work. So if you go here and you load the GeoIO package as we did in the previous talk, I will load this Beethoven model, which is just a geospatial table, right? So I can load this guy and visualize it here. So you see that this is a geotable of a statue of Beethoven, or someone may be interested in modeling and doing geospatial data science with statues. I don't know, someone may have this kind of application, right? And suppose that I want to perform transformations to this domain, right? So you see that if I execute this code, let me execute it again. The Beethoven statue is kind of laying down, right? So it's like sleeping right now. How do I rotate it so that it's looking to the scene, right? So I can, for example, take this geotable and send it to a rotate transform where I specify different rotation specifications. We support all rotations from the package rotations.jl, one of which is use rotate by analogy. There are many ways of specifying rotations, quaternions, Euler angles, all these different kinds of specifications that are supported. But one that I find very useful is rotation by analogy, which means if you know how to rotate a specific vector to some other position of your desire, right? You can just use this pair of vectors as analogy for the rotation you want to make. So for example, I don't know exactly how to represent this as a quaternion, but I know that I want to rotate vector 0, 1, 0 to the position 0, 0, 1. So I can pass vector 0, 1, 0 to 0, 0, 1 that specifies that that's the rotation I want to make by example. So if I rotate this Beethoven here, you'll see that it's now, let me just visualize it again, sorry. If I visualize it again, it will now be looking to the back wall, right? So I rotated it because I rotated by analogy 0, 1, 0 to 0, 0, 1. Now I'll rotate it once again. I'll move the vector 1, 0, 0 to the vector -1, 1, 0 so that it faces the camera, right? So if I run this again, now it's facing myself, and all the attributes that are associated with the geotable are still there, right? So I'm just operating on the geometry column, but everything that's related to the measurements that are made are still there. They're not thrown away. And you can also rotate 2D data sets. For example, if you remember, we have our GT geotable, which is over a grid, right? So I can take that geotable and rotate by a 2D angle of pi/4. And if I send this to the viewer, you see that it's just like a rotated raster, right? So it's like you have your grid. I'm just wanting to rotate this grid. It will do this in a very smart way, right? It's just going to represent this as a rotated grid without any allocation of memory. But now in the time that it plots, it just calls the appropriate Mackie function to plot a rotated image. You can also translate, and these are basic affine transformations like rotate, translate, stretch, which is basically like moving your domain in basic ways. You can also standardize the coordinates. Sometimes, for example, you want to train a model or you want to do some processing. And if you use the original coordinates that are very big numbers, I don't know, you are using something that has, I don't know, UTM coordinates or longitude, latitude, whatever scale you're using, sometimes doing operations on these big numbers can lead to numerical issues, right? So it's sometimes good practice to just standardize everything to between -1 and 1 or minus small numbers, right? So the standard coordinates will just do this. We'll just take your grid and squish it into a box of size 1 by 1. Sorry, let me get back here. So now let's go to the advanced geometric one. So advanced geometric transforms are basically the ones that don't fit in the category of coordinate transform. So what is a coordinate transform? A coordinate transform is one that takes point by point in your domain and applies the transform on each of these points. So it takes all the coordinates independently and applies it in parallel, right? Transform, translate, rotate. The advanced ones are ones that actually sometimes manipulate the topology of the domain. What we call topology is like how these quadrangles are connected to each other, how these geometries are connected. So here, for example, I'll create a polygon with two holes. So if I show here, it's just like a polygon with two holes in it. One transform that does this change in topology is called the bridge. If you do a bridge on the polygon and you specify this epsilon here, it will just connect all the holes into the outside exterior and make it a polygon without holes. So it's a very nice trick for people that work on geometric processing, because changing the connectivity like this, you now have a polygon that you can process, assuming that it doesn't have holes. Do your operation, then undo the transform to get the holes back. So we do this, for example, to do some discretization of complicated geometries with holes, right? So you see here that the holes are connected by these bridges, these small gaps, and I can specify the epsilon to do this creation of bridges. So this is one that's not a coordinate transform because it changes the number of vertices in your polygon, right? So I introduced two new vertices for each of these bridges inside and outside, right? So it's a different transformation. There are other ones that are coming from computer graphics and geometric processing communities. For example, the Taubing smoothing one is one that takes your surface and tries to smooth it out to remove some artifacts. Sometimes you get noisy surfaces and you want to just cut out all those weird peaks. So for example, take the Beethoven model and I can create this new figure with the original and the old Beethoven, right? So if I zoom here, that's my original domain, my original geotable, and you see it has a lot of detail, right? So I can zoom in here so that you see all the sharp corners. But the one that I smoothed with Taubing smoothing, it became more blur, that's the effect of the Taubing smoothing transform. So it can be useful, for example, again, if you get raw data that's like a surface, but it's all made of this weird peaks, sometimes you can smooth it out before you start doing your analysis, because you can have better results like this. So let's go now to the last set of transform, which is the geospatial one. It's a set of examples so that you get used, but these are all covered in the book. Geospatial transforms, these are the ones that consume both the values and the domain of the geotable and produce a new geotable with these two potentially modified, right? So these are very common when you're doing geostatistical work, because one thing that geostatistics does that statistics doesn't is it consumes the domain and the values at the same time, right? So sometimes I need to remove a spatial trend. So that's like kind of feeding a polynomial in space, removing that trend and working on the residual process, for example. Or sometimes I want to convert the information that's in polygons and rasterize it into pixels, because that will align with the features that I have from satellite so that I can train a machine learning model. These are all examples that involve both the domain and the features. And you can have examples of this like this one here. So I'll create a new geotable, which is just a random one again. And you see it's like a quadratic function plus noise, right? So I'm just saying, here I have a variable z over a grid, a quadratic function plus noise. And I just want to remove this quadratic trend, right? So because I only interested in studying the residual variations here. The quadratic behavior is known or is physical. I already understand it. I want to understand what's left. So I can just detrend with a polynomial degree 2, 3, or any degree and send it to the viewer. So if you do this, you'll see here that it removed the quadratic trend and just retained the residual process, right? So this, oops, I'm out of time. And then you see that this is one example. Another example, for example, if I load this data set, which is an image, right? So it's an image, a PNG image of 2 letters. There's a letter A and a letter B in this image. If you do this potrace transform, this is a polygon tracing, it takes this image, which is a raster, let's say, and it looks on all the pixels to find out what are the polygons for each of these different colors, right? So if I run this potrace transform, it will convert, as you see here, in a few seconds, hopefully. You see that the original domain here is a transformed grid, is a rotated grid somehow, with quadrangle geometries. And after the potrace is finished, which is still running on my tablet, let's see. Yeah, I wish I had a more powerful laptop. Let's see if it's gonna finish. Okay, so you see like the original domain was a grid of quadrangles and the resulting domain was a geometry set of multi-polygons, right? So I have letter A and letter B in this, and if I visualize the second geometry on this new geotable, it will correspond to the letters because the letters are in color black, right? So this is a new domain made of letter A and B together. And this new domain is made of sub-polygons, but now this data set is vector data, right? So that's a way of converting between raster and vector. And the opposite operation or transform is called the rasterize. So I can just create this geotable over this polygon. So this is vector data now. I have the variables assigned to these polygons. I now want to rasterize. I can just send this polygon geotable to the rasterize of 20 by 20. So I want to convert into a raster of 20 by 20 pixels. And it will just create this new geotable with a grid geometry which approximates the polygons, right? So this is also very common to do, and it's considered a geospatial transform because it takes the values and copies to the corresponding pixels. It also operates on the domain, and it's a more evolved operation, right? Now I want to move to the more final, and I think I have a few minutes left, but you can look it up later. It's one of the most powerful features is pipelines. So we've seen how we apply transforms independently, right? 1, 2, 3, you can just feed one after the other. But that is not what we usually do in data science. We want to create a full pipeline that's independent of the data, and then we want to feed one geotable once to this pipeline and let it do all the operations for you. So I won't have enough time to explain, but the main idea here is we've been using Julia's pipe operator to send the geotable to transforms. Right? So this is vertical bar greater than. We replace this operator by 2 new operators that are provided in this framework, this arrow, which you get with \to, \2, and this square union here, which is this joint union. It's \sq_cup. I also explained this in the book. But so if you go here and you create pipelines, what is the effect of a pipeline? So for example, I can take a transform that selects columns A, B, and C, and send just these 3 columns to the quantile, right? So I create a pipeline here. You see that this is a pipeline object. It doesn't involve any geotable. I can then send the geotable to the pipeline, and you just execute the 2 operations one after the other. I can create trivial pipelines, and you see that like there are optimizations happening behind the scenes. So if I take a pipeline and attach to it an identity transform, it doesn't do anything. So if you add an identity to any part of a pipeline, it will just be ignored because it's like nothing to be done, right? So it has these kinds of optimizations, and you can do things in parallel, right? So if you construct a pipeline with the other operator, the disjoint union. For example, I create pipeline 1, select column A, and run the indicator transform to create three categories of this continuous variable that will execute here as a new geotable, right? I can also create pipeline 2 that takes columns B, C, and D and runs PCA, right? That creates another geotable. But instead of doing this step by step, I could just create one pipeline, the pipeline that takes pipeline 1, disjoint union with pipeline 2 that creates a parallel pipeline. As you see here, it's represented by 2 sub-pipelines of sequential transforms. And I can just feed my data to this whole pipeline with parallel branches, and we try to parallelize things as much as possible. So there are always room for improvements, and please feel free to join in the code and see if there are more parallelization opportunities there. But you see, like, if I just feed one geotable to this pipeline, it will take column A, it will break into 3 indicator functions, apply the quantile, that's these 3 columns. It will take column B and apply B, C, and D, and apply PCA and return these 2 PC components. So you can quickly build very complicated pipelines, and they work with grids, with vector data, with unstructured meshes, with everything in the same syntax. So the idea is that you create these pipelines and reuse them after. So let me just finish here. These concepts of reversibility, geospatial split, apply, combine, geospatial joins, they're all covered in the book. They're not covered here. We just covered the concept of transforms. But you have total access, as I mentioned, if you just Google geospatial data science with Julia to get access to these other concepts. And if you want to get involved, again, like the purpose, I think one of the purposes of being in a workshop is being present with the person, right? So come say hi. I'm here the whole week. I'll be happy to brainstorm ideas. The book is the best resource to get more involved because you know what's the message behind the framework. If you want to, or you believe that this is a good effort, like give us a star on GitHub, share on social media. It really helps because the community is small, so any help is valid. If you want to get support from our open source community, right? So there's a Zulip channel where you can join, #GeoStats.jl, and you can contact me as well if you need something more dedicated, right? So we are open for that as well. If you have questions, I don't know if you have time, please feel free to ask. Thank you very much.
I really like this pipelining. I find it a very beautiful way of thinking about an operation but not yet applying it. I was wondering so you mentioned you implemented that for this 2 operator, and because Julia has this circle for plotting functions, right?
Yes.
How is that different?
So the composition in Julia, like the circle you mentioned, is eager, right? So it's eager evaluation. So if you compose a function like this, it executes the function 1, gets the result, and apply function 2 to the result of function 1. So it's like applying functions and getting the intermediate results generated, right? What we're trying to do here with pipelines is lazy evaluation in the sense that we build the pipeline and try to do some extra optimizations in the pipeline level before we send the geotable to it. So the main difference is like compositions in Julia with the circ, \circ, or the Julia's pipe operator. They're eager evaluation, and we are trying to be more lazy with the 2 operators we created.
Okay, so it's more like a performance thing than like conceptual difference.
Also, I think it would be not just performance, but I think expressivity maybe too. I don't know, because because the circ is only the sequential one, right? So if you use the circ composition, you apply one transform after the other. The other operator that I provided, the disjoint union, allows you to create branches that operate in parallel. So you get one single geotable in, you branch, and you create many geotables that join at the end into a final result. That's not possible with just the circ operator.
Yeah, and then just related to that, So the individual elements of the pipeline usually create, I guess they're actually functions, right?
There are structs, there are types.
They're types. But then sending it to the pipe, have you defined some kind of like functor to it? So
Exactly.
Okay.
They're functor structs, exactly. That's the design pattern.
Okay, so something like this, whenever you said like replace, for example, that's why you write it with a capital R, because it actually creates that, at the moment you call it, it creates a struct.
Exactly.
Which has a function to attach to it, and so you can have that.
Exactly.
Yeah, very nice.
Mm-hmm.
More questions?
That's all?
Okay.
Awesome.
Thank you, Julie.
Thank you.
Julie, not Julia.
That was a cool one.